Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, okay, let's start. So in our problem, we're going to have a player, and player is synonymous with maybe an agent or a learner or a decision maker, and this player plays in the world, and sometimes we call the world nature or the environment. And I'd like you to imagine, maybe an application of an algorithm that's making some automated investment decisions for us and handling our portfolio, and the world is the stock market, or maybe a spam filtering algorithm that's observing a stream of spam emails that are coming in, and it has to determine which ones are spam and which ones are not. So that's the player in the world. And then in machine learning, we like to make these assumptions that the world is simple. We either assume that the world behaves like some stochastic process, very often an IID stochastic process. In online learning, we like to say that the world is oblivious, which means that the world doesn't react to us. And then we do have some formalizations of worlds that react, but often we assume how they react. And I want to make the point that this is often an unrealistic assumption. I mean, when we work in the world, when we make choices, when we make decisions, the world reacts, and it's often in a way that we really can't model in any good way. For example, if you think of the spam filtering example that I gave, as I manage to detect spam better and better, the spammers are going to notice that, and they're going to change their strategy. This is a little bit of an arms race going on. So as I improve, as I make better decisions, they get better as well. If you think of the online investment or the portfolio management problem, then also, what's the world? The world is the thousands of other investors that are trying to make a profit at my expense, right? It's kind of a zero-sum game in some sense. Or I mean, they want me to lose so they can win. And they are strategic. So the world is not IAD. They're trying to hurt me. So the assumptions are unrealistic. And the problem is we don't really know how to model them very, very well. How does the world react to my actions? And in this talk, what I'd like to ask, the question I'd like to ask is, how far can I go if I assume that the world reacts to me in the worst possible way? So in fact, the world isn't the world. It's an adaptive adversary. It's a bad guy. And this guy's malicious. He knows my algorithm, so he knows the pseudocode of the other algorithm that I'm going to run, and he has infinite computational power. So let's assume that's the world, and if I can deal with that guy, then I can certainly deal with the real world. So that's why it's an interesting question to ask. So this is going to be the topic of the talk. Now, let me explain how the player interacts with the adaptive adversary. So there's a little protocol that goes on here. It's a repeated game. First of all, I want to assume that the player has the power of randomization, and this is critical. So the player has access to random bits, and the player has to perform, one of a finite number of actions. So here they're depicted by these slot machines, by these arms. So the player has to choose which arm she pulls. And this is a repeated game, so it goes on for a while. Let me describe one round of the game. So round T of the game. So T minus one rounds have already finished, concluded, and they've played those rounds, so they've learned a little bit about each other. The player has learned about the adversary, and the adversary has figured out a little bit about the player. So here's round T. It starts when the adversary chooses a loss for each one of these possible arms, and then immediately conceals them. So the player doesn't see what the losses are. Then the player defines a probability distribution over the arms, draws some random bits, and according to the distribution, chooses the arm that she wants to pull. So she pulls the blue arm, and she suffers a loss of 0.8. So she gets to see what this loss is, and she doesn't get to see what the other losses are. And this is why we use slot machines. I mean, this is the idea that when you pull one of the arms, you don't know what you would have gotten had you pulled any one of the other arms. And this is called bandit-feedback, and the name is for historic reasons. It's because these slot machines are nicknamed one-arm bandits, so this is called bandit-feedback. It's when I only see the value that I actually suffered. I don't see the loss that I would have gotten if I'd pulled something else. So this is the game they played. There's another game, similar game, which is called the full information feedback game, which is the same thing, but there's one additional step at the end of the game, and that's a step where the other loss functions are in fact revealed. So when at the end of each round, the player sees what would have happened had she done something else, that's called full information, and if she doesn't, that's called bandit feedback. And we're going to talk about both these settings kind of in parallel. So let's define things a little bit more formally. So this is the K-armed online learning problem. So it's a capital T round repeated game. So let's assume that capital T, the number of rounds that's going to be played, is known in advance and agreed upon between the adversary and the player. The player is randomized. The adversary is a deterministic adaptive adversary. So he's adaptive. He sees what the player plays, and he adapts his strategy based on what the player does, but he does so deterministically. So here's the more formal way to state the game. So first of all, the notation. The player has an action set, one of k actions. And here's something that makes things simpler. So we can notice that the adversary, because we assume that he's deterministic, we can actually have him do all his decision making before the game begins. So, right, he has infinite computational power. He knows the code of the pseudocode of the algorithm that the player is playing. So he can run all these simulations beforehand and just specify to us before the game begins how he will react to any sequence of actions played by the player. So this is exploiting the fact that the adversary is deterministic. So actually, the adversary doesn't participate actively in the game itself. Before the game begins, he defines a sequence of t loss functions, where each loss function is a function of the entire history. So this is how we have him specify how he's going to react to the player's actions. Okay, so he defines t functions. Ft takes t actions, the history of t things that happen until time t, and maps it to a loss. And now the game begins, and only the player actually plays in the game actively. So for t rounds, what happens is the player chooses a distribution theta t over the action space, draws the action, and then suffers the loss f sub t, defined by the adversary, evaluated on the concrete sequence that the player played. So of course the player doesn't get to see the loss functions before he plays, right? These are kept secret from him, but they're well defined for the purpose of our formal setup. And then the full information feedback game, again, is one additional step that happens here, and this is at the end of the game, the player actually gets to observe for every possible x, what would have happened had I played x now? I don't get to see the counterfactual of what would have happened if I had, changed my strategy from the beginning of time, but today I get to see, what would have happened had I done something else. Here are two examples just to motivate. So bandit-feedback, here's one little toy example. Online content optimization. So I assume that I have a news website, and my editors or my reporters give me a bunch of different articles, and I can only advertise 3 of them on the top of the page. Which 3 do I show? And I want people to click on these ads. So I choose 3 to show. Some user comes to my website, I show these 3 little ads, and then either I get a click, which is great, so that's a loss of 0, or no one, or the guy doesn't click, and that's a loss of 1, so that's bad. But I don't know what would have happened had I shown some other set of ads. So that's the bandit feedback example. And the full information feedback is also very realistic. So this is an example of investing in one stock. So let's say that I just want to own one stock every day. So I choose one stock, I buy it, I own it. But at the end of the day, I know how good the stock market, I know how much money I would have made had I invested in some other stock. So I get full information in this case. So this is just a little bit of a motivation. Okay, so now let's say I have a player. How do I evaluate the quality of this player? So first, let's define the expected cumulative loss of the player. So what we do is we just sum up over these t rounds the loss suffered by the player. We take expectation because the player plays randomly, and we define L of t to be the loss accumulated by the player over the rounds of the game. But notice that this really isn't meaningful. We didn't restrict the adversary in any way. The adversary can, in fact, assign a maximal loss to all actions. So he can, inflate my loss as much as he likes. That's not interesting. So we need to compare to something. We need a reasonable basis of comparison. We need to compare to some alternative which makes sense. And I'm going to use the very, very simple comparison, which is to compare against constant actions. So I'm going to say, how much do I regret not just sticking to maybe the blue arm and just pulling that for the duration of the game? So I choose one action, and I say my regret for not having chosen and played this action throughout the entire game is just the amount of loss in expectation that I suffered minus the cumulative loss that I would have suffered had I played that action again and again. Now, my regret against the best action is, again, my cumulative loss, the difference between my cumulative loss and the loss of the best action in hindsight. So after the game is over, assume that all the loss functions are now exposed. I can say, if I'd only played this one best action all the time, this is what I would have gotten. So this is my notion of regret. Okay, so that kind of clears up the problem of the adversary can artificially inflate everything. If he inflates everything, he'll hurt me and the competitor equally. So this is the notion of regret, and what we're going to try to do is bound regret. We're going to prove these bounds on regret. So notice that as the game goes along, I accumulate, the regret accumulates, the loss accumulates, and the regret can grow, and the question is, how fast does it grow? So if the regret is guaranteed, if I can prove to you that it grows only sublinearly, so maybe it grows like, big O of t to the power of q for some q less than 1, it means that as time is going by, the gap between me and the best arm in hindsight is shrinking. I'm doing better and better. So I'm learning. I'm improving. On the other hand, if I can prove to you that the regret is lower bounded by a linear function t, it's omega of t, then I'm not learning anything. It means that on all rounds, there's still a big gap between me and the best guy that persists for the entire game. So I'm not learning. So these are the two kind of things that we want to talk about. And then q, the exponent here is the learning rate. Smaller is better. If we have a smaller q, we're learning faster. Okay, so we've defined regret, we've defined the game. Can we prove some bounds on regret? So yes, here's the first result. It's kind of depressing. No, we can't learn. So there always exists an adaptive sequence of loss functions such that my regret grows linearly. It's impossible to learn against adaptive adversaries. So how do I prove this? Well, I can just tell you what the adversary does. I can define to you an adversarial strategy, an algorithm for the adaptive adversary that will cause me to suffer linear regret. So here it is. He knows my pseudocode. He knows my code. So before I've seen anything, he knows the distribution that I'm going to start out with, right? So the player on each round defines some distribution of the arm, and theta 1 is just this distribution in the first round before having seen anything. So he just chooses some action with a positive probability. And now he defines his adaptive sequence of loss functions as follows. He ignores everything but the first action. So it doesn't matter, when t equals 2, 3, 4, he only looks at the first action. If that first action was this x hat, which there was a positive probability of that being, then the loss is 1. Otherwise, the loss is 0. So he doesn't care if I prove, he doesn't care if I learn. He just looks at my one first play. If that was x hat, I will suffer a unit loss forever. So after t rounds, I'll suffer a loss of t. I'll accumulate t units of loss. There's some positive probability of that occurring. So my expected loss is t times that positive thing. What's the alternative? The best action in hindsight could be anything which isn't x hat. If I had just stuck to that, I would have suffered 0 throughout. So the regret, indeed, is t times this constant. So very, very easy. That's the adversary, and I can't learn. So why did we bother and set up all this thing? So we'll do what we always do in computer science or in machine learning. When a problem is too hard, we just have to make it a little bit easier. We have to restrict the adversary just a little bit. So this is the class of all adaptive adversaries. We have to restrict it. We can't, we showed a point in here which causes me to suffer a linear regret. I can't learn. So here's another little subclass in there called oblivious adversaries. So oblivious adversaries are a very special case of adaptive adversaries. They, in fact, do not adapt. So they adapt in the trivial way, which, in fact, they don't. So let's define that. Oblivious adversaries are adversaries that don't rely on the past. So we'll still use the same notation. The function still takes the entire history, but it ignores the first t minus 1 actions in that history. It just looks at my current action. So formally, for any sequence of t actions and any other prefix of the sequence of t minus 1 actions, if I take these first t minus 1 actions and replace them by the other guys, but this last one is the same, then the loss is the same. So this is an oblivious adversary, and this is in fact the standard assumption in 99% of papers on online learning. So we like to assume that the world is oblivious. We can use the convenient shorthand that, since we only depend on the last guy, we can just write f and just give it that one argument. And then our definition of regret simplifies to this simpler thing. And you'll see this in most papers. Most papers will use this kind of abbreviated notion of regret. But just keep in mind that if we don't assume that the adversary is oblivious, then this kind of doesn't make sense. We have to revert to the more complicated one that uses the full expressive form. And you'll see actually quite a few papers that talk about adaptive adversaries and use this notion of regret. And you should be very suspicious of those results. So this only makes sense in the oblivious case. Okay, so just to, again, give an example, when is it reasonable to assume the world is oblivious? So let's say I'm investing $1,000 in a stock. No one cares. The world isn't really going to change by my little investment. If I'm investing $100 million in a stock, the stock market is going to react. It's going to change. So a big institutional investor cannot assume that the world is oblivious to his actions. He can't assume that he's some negligent little speck of dust and doesn't affect the world. His actions will cause the world to change and will affect his losses in the future. So I don't know, is this true? I didn't know if to say a billion or, well, anyway. I've never invested $100 million, so I don't know. Okay, so we have oblivious adversaries. This is online learning. This is impossible. Let's define some intermediate steps in between. So the first one I want to define is the switching cost adversary. So what's that? It's more general than the oblivious and less general than the adaptive. So an oblivious adversary with a switching cost is like an oblivious adversary, but he charges me an additional cost of c, some constant switching cost, whenever I change my action. So whenever my action on time t is different than my action at time t minus 1, I pay an additional loss of c. Or in other words, he defines this oblivious sequence, which only depends on the current action. And then the real loss is that oblivious loss plus c times the indicator function of did I change, did I swap arms. And again, the example is that maybe I'm investing a little bit of money in the stock market, so the stock market is oblivious, but maybe I pay some transaction costs. So, you go on the web, you pay $7 for a commission for each trade. You don't want to hop around every day between stocks. Every switch from one stock to another costs you a little bit of a penalty. And this, notice that this loss relies on the current action and on the previous action. So we say that it has a memory of 1. Whereas in that counterexample, remember that? He remembered all the way, every iteration, he penalized me for the very first thing I did. So switching costs, they have a memory of 1. So they're a special case of adaptive adversaries that only look at my current action and my previous action, which are a special case of adversaries that have a finite memory. They can look m steps back in time, but they can't look all the way infinitely back in time. So this is the little hierarchy that I want to talk about. Just to mention, I mean, most of machine learning is here, right? Most people like to assume this IID thing, online learning is this, and I want to talk about that. Okay, so now we have a table, and when theoreticians see empty tables, they get really excited. They have a little sparkle in their eye because we have to fill in these values. So what is this table? Here are different types of adaptive adversaries. We want upper bounds and we want lower bounds on regret in the bandit, feedback, and the full information case. I have to make some technical assumptions just to fit everything in a table because I'm going to refer to previous work in other papers, and sometimes the assumptions are a little bit different. So I won't go through the details of this, but I'm just going to make two very general assumptions. One is bounded range, which means that whether I choose this action or that action at time t, the difference isn't going to be unbounded. There's some bound on that. And then bounded drift means that if I play action X today or tomorrow, again, there's not going to be a huge gap between them. So these are necessary. You can't go without them, but let's skip that. Okay, upper bound of t is trivial. I just said everything is bounded. If I just pay any action, the regret I can accumulate on each round is bounded by 1 or some constant. So if I play t rounds, I'm going to have a regret of t. We proved a few slides ago that in the fully adaptive case, I can't do better than that. So here I have a perfect characterization. When these two things are equal, then I understand it, right? So I understand this so far. Now I can take all the previous work done in this field. So a bunch of papers, and they prove a lot of things. And again, online learning is what we understand, or classic online learning is what we understand the best. So here we have a very good characterization. We have square root t, again, a sublinear growth of the regret. So we do have a nice, quick learning upper and lower bounds match, both in the bandit and full information case. So this was the state of the art when I started working on this problem, based on 10 years of past work on online learning. And then the nice thing about this table is that when you have one problem is a special case of another problem, then the lower bound, of course, applies. So lower bounds propagate this way, and upper bounds propagate that way. I mean, if I could get t to the 2/3 on any guy with a bounded memory, certainly I could get t to the 2/3 on a guy with a unit memory, right? So whenever we have a result here, it kind of propagates this way. So this is the state of the art. I want to talk about two results. One is a result I had last summer with Raman and Ambuj. And there, we used a blocking technique to give an algorithm that achieves t to the 2/3 against bounded memory adversaries in the bandit case. And again, bam, 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 this thing propagates to the left. So blocking just means that we take a standard, off-the-shelf online learning algorithm and run it in blocks. So it chooses some action and sticks to it for the duration of the predefined block, and then only at the end of the block does it change to a different action. So intuitively, that would reduce the number of switches, but we can also prove that it actually works better against, that also works against memory-bounded adaptive adversaries. So this is the first result. And now very, very recently, so hot off the presses, this is just this summer, with Nicolo Cesa-Bianchi, who came as our visitor to Microsoft Research, and Ohad Shamir from the New England, he's now in our group. So he used to be in the MSR New England, now he's moving to our group. So this is yet unpublished work. And we prove this lower bound. So it's the lower bound on the number of switches. So again, we're looking at the bandit feedback case, and we're asking how much does an oblivious adversary who penalizes me for the number of switches, how much does he pay? And we showed that in order to get something better than t to the 2/3 regret on the oblivious part of the loss, we have to make at least t to the 2/3 switches. So this is how we prove that. And again, you have this magic propagation to the right. And there's also this non-trivial propagation of y. This implies that. It's very simple, but I can't go into it right now. So how do you prove these lower bounds? I just want to say one word about that. I have to prove the existence of an adversary. Remember when we showed this lower bound, I just told you what that adversary is. I don't know what this adversary is, but I have to prove that he exists. So we used a very convenient technique that is called the probabilistic method. And there, if you want to prove that something exists, the way you do it is you define some probability distribution. So here it's a distribution over adversaries or over sequences of loss functions. And you show that there's a positive probability when you sample from that distribution of getting a sequence of loss functions that will inflict this much damage. And if there's a positive probability of finding that guy, then he must exist. If he doesn't exist, then there's probability 0 of finding him when I just sample randomly. So all we have to do after using this technique is to define what is this probability distribution. And the one that we used is just a Gaussian random walk. So you define 2 arms, and they just hop around doing a Gaussian random walk, and then we do some theory and prove that that's enough to show that with positive probability we'll get a guy that will hurt us that much. So this is now the current state of the art. You can see that it's all tied up here. So we understand what happens with switching. We have an upper and lower bounds on regret that match up for one memory, for M memory. We have one little glitch here, which is in the full information feedback case, we're not exactly sure what the situation is when you have one memory, but when you have a memory of 2 or more, we already understand it perfectly. So we almost have a perfect characterization of what's going on. The super interesting thing that just pops out here is this. So you can see that there is a fundamental difference between learning with bandit feedback and learning with full information. And this isn't trivial, because, maybe intuitively it's trivial, but what we knew before is they always look the same. Somehow, bandit was always a little bit, a few years delay until the paper came out, but you often saw that the regret behaved the same in bandit and full information settings. So here we have a very, very clear indication that the bandit case and the full information case are not the same. So let me summarize. The world reacts to our actions. We ask the question, how far can we go under the paranoid assumption that the world is out to get us? It reacts in the worst possible way. We model this problem as online learning against an adaptive adversary, and then we derive an almost complete characterization of policy regret in this setting, and we got this very, very interesting result, which shows that bandit feedback and full information feedback have a qualitative difference to them. And that's it. Thanks. Are there any questions? Yeah. Better.
So, within the release setting, for example, take the case of spam, right? In the case of spam, your move is actually not classifying particular spam, but a whole filter. So in the case of link spamming, it's a whole new ranking function.
Okay.
So your move is not,
Sure.
So there's a very large number of possible moves right there.
Yes.
And your learning is choosing that.
So right. I made things very easy for myself. This thing completely ignores the dependence on the number of arms, and certainly none of this works if the number of arms is infinite. This is, I have research on this, but it wasn't presented in this talk.
That's my question, right? So what happens in that case?
It's each result is different. They all have a polynomial dependence on the number of arms. Is it logarithmic or square root, or is it linear? So we have to go into each one of the result and kind of refresh our memory about it. Here, I really just cared about how these things develop with time. But definitely, the dependence on the number of arms is an active, an interesting field of research that I'm engaged in. Another one is, I just compared against constant actions. That kind of sucks. So can we find more interesting comparison classes? And certainly we can do that. We can define structured comparators. When we define deterministic Markov decision processes, we can compete against constant actions that occasionally are allowed to switch and so on. So we have all those results, but I just didn't have time to go into them. And we certainly don't have this beautiful kind of complete picture there. Yeah.
I have 2 questions which are about the same. So the first one is, what's the dependency on M? Because if you lose linearly on M, then it's kind of like...
You lose linearly on M?
Yeah, do you?
Yes. When you use yes. So when...
Even in the lower bound?
The lower bound, I don't know. The lower bound is 2 arms. We can show, so we just needed to show an adversary that gets this dependence on T. So we just had one with 2 arms. I don't think we really thought through the thing. But the upper bound definitely, this upper bound definitely depends on M linearly. And linearly is good because when you take MDP, kind of reinforcement learning type of algorithms, they will sometimes have an exponential dependence on the history, because the number of states is 2 to the, or number of actions to the power of number of history length. So you're linear in the number of states, which is exponential in the memory size. So actually,
policy is much more complex there. Right, so policy is also exponentially large. So
yes,
it's not
right.
a fair comparison in the sense.
You're right. Yeah, you're competing against policies and not fixed actions, and that's
right.
like the higher bar. Yeah.
So the other question is, do you have like a linear setting bounds for this memory when you have a memory? So for the featurized case, I guess. It goes back to Peter's question, like linear bandits type generalization.
These results, okay, so you're asking me, so here we had a discrete choice type of setting. We had one of a finite number of actions. What happens, so I mean, many of the upper bounds, so these upper bounds work for pretty much any online learning setting. The lower bound is, very, very specific to 2 arms, which is good enough for this. I don't think, and it's also very recent work, so I don't think we've thought about how this affects the linear case, but the upper bounds always work. Yeah?
I have a question about, is there something about opposite situation, cooperative bandit? For example, I am analyzing click-through rate, and I want that user choose optimal advertisement. And user cooperated with me, he also wanted to choose optimal. And let's say he found that my advertisement in reality not on the first position, but on second position. So he becoming his strategy, modify his strategy, clicking to second position. So he is not IID, but he is going to get maximum click-through rate. So is there some theory to improve IID to cooperative bandit?
I don't know. I'd have to think about that. I don't know. Let's take it offline and chat about it. I'm not even sure I fully understood who cooperates with who. I mean, in this world, it's me against the world, right? Everyone's against me, and I'm running away. But let's definitely take it offline. Okay, so now I'm putting on my organizer hat. So we have a lunch, and here's how it's going to work. Is there something I need to know?
If you like a vegetarian option today, we have those actually set aside out front, out here. And so if you want to keep it this way for vegetarians only, and then you can actually know what your options are.
Okay, so here's how it's going to work. So we have 3 stations that are giving out the food. One is right behind this wall, so it's out these doors and to the left. Another one, the other 2 are in the 2 rooms that are just opposite here. So if we go around this way or that way, you'll see there are 2 other smaller classrooms, and they're set up with tables, and there's food there. What I'd like to ask is if you're sitting on this side of the room, if you could please go out of these doors, and then either take a left or a right and get to that room. And if you're sitting on this side of the room, if you could please exit through those doors and go around. And again, you could go to the first room or the second room. The atrium of the building is open to us. So once you take your food, you can either sit in one of these 2 rooms. Anywhere you see a chair, you can sit down. You can walk out of these glass doors, and there's a big atrium there. You can sit there. There are security guards that will prevent you from going where you're not supposed to go. So the algorithm, if you find yourself in a headlock or in handcuffs, then you know that you've gone too far. Please go wherever you like. There are soft drinks at the end of this corridor. And bon appetit.